Hi, my name is Camille. Do you know what a fractal is? Fractals are everywhere, from the various shapes determined by equations to the plants we see every day, the mountains of the world, and even the coastlines of the very continent we live on. But what really is a fractal? Let's put it into perspective. You're in an elevator with mirrors on both walls. When you look into the mirror, what do you see? Images and images of yourself. Infinite renderings of you as you look into the glass. That is the very basic idea of a fractal. Here's another example. In this plant, you can note its general shape, but as you look closer, you notice something. The leaves which stem outward from the plant seem similar to the entire frond. They are self-similar to the original, just on a smaller scale. Already we've seen 2 examples of fractals, and we haven't even gotten to any math yet. Wow! Now for another example. Long ago in the 20th century, an English mathematician called Lewis Fry Richardson was studying the length of England's coastline. While making his measurements, he realized one particular thing.
If we measure England's coast with a large measuring tool, we get a set value. However, if we use smaller measuring tools, we can account for more irregularities in the coastline, thus producing a larger value than the initial. The more we keep doing this, the more our value increases. And as we continue our observations, we can measure how long each of our measuring tools was and how many of them we used. And you will find that the smaller the measuring tool does indeed produce a larger value for the coastline. As you can see, measuring with a pair of peppers produces a larger value than that of the single spoon which we used to measure the initial value. And the smallest of our measuring tools, the Lego Star Wars minifigures, produce an even longer set value for the coastline, since they take into account all the irregularities.
Richardson realized that, rather than converging towards a particular number, the value of the perimeter diverged to infinity. Essentially, he concluded that it was an infinitely long coastline containing a finite space. This theorem, you might notice, is similar to that of Zeno's half-distance paradox. Most importantly, it was the beginning of the mathematical development of fractals as we know them. Before we go on, however, let's introduce the 3 properties of fractals, which we've explored with our 3 examples. First, with the mirror, we can see that fractals are recursive, repeating on and on infinitely. Second, as we saw with the plant frond, fractals are self-similar, meaning that as you look closer and closer into the fractal, you can see the shape of the whole. Finally, Richardson's coastline paradox introduces us to the 3rd property of a fractal, its fractal dimension. As we saw with the increasingly smaller rulers mapping out a more detailed coastline, fractal dimension is essentially a way of measuring a fractal's complexity. It may be in between 1D or 2D, or even between 2D and 3D. This strange concept was developed further by mathematician Benoit Mandelbrot, who we'll talk about later. Now to review, you know that fractals are shapes which have recursive, self-similar extensions of themselves and fall into the category of fractal geography. Excellent! We haven't even gone over 5 minutes, and we've already discussed the basics of fractals. Look at you!
That's good. You've taken your first step into a larger world.
Now we will talk about the mathematical aspect of fractals. High school students Camille and Daniel have won our localized school support fund representing St. Martin's Choir School. They have submitted a video on the mathematical aspect of fractals. Please enjoy.
Hi, my name is Daniel.
And I'm Camille.
And we're going to tell you about the equations for the Mandelbrot set and the Julia set, 2 fractals. Fractals can be created in multiple different ways, but the most common is to iterate some rational equation over and over and over again and see how the values change over time.
So, first, start with a complex number plane, with the real numbers on the horizontal side and on the horizontal axis and the imaginary numbers on the vertical axis. Then choose any point on this graph and iterate it multiple times with the equation z squared plus c. You would do this by starting with z equal to 0 and setting c equal to the point on the graph. Then, after each iteration, set z equal to the result from the previous calculation. If after doing this an infinite number of times, the numbers diverge to infinity, then that point is not part of the Mandelbrot set. If, however, the numbers stay bounded and converge to a single point or a cycle, then that point is a part of the Mandelbrot set. If you then repeat this for every single point on the complex plane and color the points that stay bounded black and the points that diverge to infinity some other color based on how fast they diverge, you get the famous Mandelbrot set.
And now, the Julia sets are created in a similar process, but instead of setting z to 0, z is set to the coordinate itself on the Mandelbrot set. Meanwhile, on the complex plane. Meanwhile, c is set to any complex number of the entire fractal. So, by starting with different values for c entirely, you can get a completely different Julia set for any specific point on the Mandelbrot set. And that's the amazing thing. This formula is used to create artwork, some sorts of digital art, anything really, because you can really get anything you want on any point. This is Fractals.
Today, we are in Daniel Garcia-Moreno's backyard. We continue our search in this modern Eden for the natural fractals of the real world. And I think we're getting close to something. Could it be? Look at these. Look at the shape of the fern. And then as you observe a frond, you see that same similar shape. This is the self-similarity we've always talked about. And look, you look at each little leaf on each frond and the repetitive self-similarity. I can't believe it. We found a fractal in the natural world. Look, this here is a... And the tree, goodness gracious, it's also a fractal. The branches are extensions of the trunk, and onto those branches, twigs, and even more, and the clouds too. And the very land we stand on. Look, it's as you go closer into each formation, fractals upon fractals. There are so many fractals around us, and I never realized it in this world. The trees, the sky, the cloud, the land, so many things are fractals, and we never notice them. It's wonderful. It's absolutely an incredible
Get up, my lord!
Guys, for that interruption. And now we return to our regularly scheduled program.
This just in! Fractals are amazing! What do you think of this newsreel, Camille?
Wow, that looks really interesting, Daniel. Why don't we show our viewers?
Fractals are everywhere. Every day, they are being applied throughout the world, forming a part of industry, of geography, and even of art.
There are so many ways nowadays that people can apply fractals. Let's take a look at some.
Fractals are being used to model many plants found in nature and explain why they look the way they do. Because of the repetitive and self-similar properties of fractals found in plants, they require less DNA to store, thus lowering the amount of energy required for organisms to reproduce. This accounts for self-similarity in flora.
They are also used to compress images and videos. By analyzing images for repetitive and self-similar sections and representing them mathematically, the file size of some types of images, namely those of textures and images of nature, can be greatly reduced.
Wow, hopefully it can help storing all the Instagram reels I have.
Not likely. Anyway, many radio antennas are also modeled after fractals, such as the Sierpinski triangle and carpet, the curve, or the Hilbert curve. Traditional antennas are bulky and can only receive a very narrow range of frequencies. This is because the frequencies which an antenna can receive are dependent on the size of the antenna in comparison to the wavelength of the radio wave. Because fractals have repeating features at multiple scales, they can receive a much wider range of frequencies. They are also much smaller than traditional antennas, making them ideal for use in small devices such as phones.
The concept of fractals can also be used to analyze properties of geographical and geological formations such as the roughness of coastlines, using the same method of calculating the fractal dimensions from the video of those two St. Martin's Choir School students, which has gone viral. We can calculate the dimension of different coastlines to compare how rough they are. For example, the roughness of Norway is 1.52, while the roughness of South Africa is 1.05, meaning that its coast is much smoother compared to that of Norway. Meanwhile, Great Britain has a fractal dimension of 1.25, making it a lot more rough than that of South Africa.
Finally, fractals can be used to create very realistic and detailed virtual environments in video games and movies. Because of their frequent appearance in nature, they can be used to generate terrain, trees, and clouds that look like they are real.
Which brings us to our next talking point. Amazing Strange Rope Police sales have been booming. Fractals are everywhere, growing in the soil, high in the sky, the very earth we stand on, and even our own selves. Happy students like these continue to learn at school, and the sun shines bright on the world. Although life is often simple externally, there are so many wonderful and amazing things which make up our world today. Fractals are just one of these strange concepts among us, of which we have been able to explore a great deal over the last 50 years. And as you continue in your daily lives, just remember and look out for them. Fractals are all around you,